Hello everyone, welcome back. In previous lecture, I explained about the terms related to balancing of locomotive and what is the effect of partial balancing in locomotives. I explained about the variation of tractive force, that is Ft. Then there was Fs, sorry, first one was Ft, that is tractive force. Then there is Cs, which is swaying couple, and I discuss about the hammer blow effect in the locomotives. So basically the tractive force was the resultant unbalanced force due to two cylinder along the line of stroke, while the swaying couple, when the two cylinders were there along the horizontal direction, there will be the couple formed due to that unbalanced force, that is due to the tractive force. And the third one was hammer blow, and that acts perpendicular to the rail. Now we will discuss some of the example. For that, we will use the formula derived earlier. So first let us see our first example here. A two-cylinder locomotive engine has following specification: the reciprocating mass of parts or mass or per cylinder is given by 300 kg, that is our m, small m. Then there is crank radius, small r, is given in mm, and we have to convert into meter, so it will be 0.29 meter. Then the angle between crank is given, it is that is theta 90 degree. Driving wheel diagram is 780 mm. So driving wheel sorry, here it is printing mistake, this is not diagram, this is diameter of driving wheel, which is 780 mm. So the radius will be half of it, so it will be around 890 mm, and we will convert in meter, so it will be 0.89 meter. After that, the distance between cylinder center is 640 mm, so it will be converted, that is the length, capital small l, and it will be also converted into meters, so 0.64 meter. After that, there is distance between the driving wheel plane, so that is given by the small a. तो प्लेन के बीच का डिस्टेंस है, that is small a, and that is also 1.53 meter. 1.53 meter. We have to find the fraction of reciprocating mass, that is our small c, that is the fraction of reciprocating mass. We have to find small c, we have to find to balance if the hammer blow is not exceeding to 45 kilo newton. The hammer blow value is not exceeding the 45 kilo newton. Now, so at 95 kilometer per hour, so that is our omega 95 sorry, where this is the speed velocity v, and that is 95 kilometer per hour, and we know that v is equal to r omega, so we will find the omega and we will put in that equation m omega square r. So we can find the omega sorry f v, and we can find the balancing mass and this fraction c. Second thing we have to find is the variation in tractive effort, that is given by the ft equation. The equation for ft is plus or minus under root 2 m omega square r 1 minus c. We will use this equation. Third thing we have to find is the swaying couple, that is given by the cs, and the equation for that is plus or minus l by root 2 m omega square r 1 minus c. And the hammer blow equation is, hammer blow का जो equation है, that is FVU, the vertical force, that is m omega square r, and this is the balancing mass, and this is also balancing radius. So we will use this and find our solution. So here the first, there is the given data that I already discussed about, and we will see. First we have to prepare the table. So here we can see there are 4 masses A, B, C and D. First one is MB1 and last one is MB2. The second B and C is 300 C, and C is also 300 C. So the mass is here given for both the cylinders. So we know that m, radius of rotation is given, the distance between both, that is radius of crank, is 0.29. RB1 and RB2 are unknown. So first, centrifugal force in kg into meter we can find by this. Then there will be the distance, because here only partial mass is considered, that why C is taken, because we are partially balancing, not complete balancing. So only 300 of the C. Complete total mass is 300 kg, but only some portion C fraction is considered as the balancing. So 300 into C. We have to find this value, how much portion we are balancing. The distance from reference plane is given, that is 0.44 for second plane, then third plane it is 1.08, and fourth plane it is 1.53. Now next thing, we have to find the couple and the angles, that is theta 0 and 90 and theta b. The couple we will use, and we will form the couple diagram. This is the position diagram as I have explained in the table. We can see from the position diagram the distance is also given. The total distance is 1.53, and distance between the crank and wheel is given. Also this is given. This is the crank position in the angle, there is 90 degree between both the first and second crank. So we can find this. We have taken A को हमने रेफरेंस प्लेन लिया, सो यहाँ से डिस्टेंस स्टार्ट करेंगे 0 और इस डायरेक्शन में लेंगे तो सारे के सारे डिस्टेंस हमको पॉजिटिव मिलेंगे. ठीक है. नाउ we will draw the couple polygon, and here the closing side of couple polygon will be the our CD, that is the resultant, and that is given by the under root CB square plus under root CC square, and we can find it by this equation. Here CD is equal to under root CB square plus CC square, and the C is taken common from here, and we can find the CD value. Now we know the hammer blow equation, FVU is equal to m omega square r. So for same both cylinder it will be same. Velocity is given in kilometer per hour, so we will multiply into 1000 divided by 3600, so it will be meter per second. Then we know that V is equal to R omega, so omega will be equal to V by R, we will get in radian per second. After that we will put the value in this equation. MB2 is unknown, we don't know the value of MB2. RB2 is also unknown, so we will combine both term and put over here. FV we know that in kilonewton it was given, so 10⁻³ in Newton. Then omega we have found over here, so we can find ultimately the MB2 into RB2. Now next thing we have to do, we have to compare this with this equation. So it is this equal to this. So by if we put the value of equation number 4 into equation number 1, we will get MB RB as equal to MB RB. We know that the value 51.18, so we will put over here in this equation. So here we will put and we will get the value of C. That is our first answer, that is the fraction C. Then there is second thing we have to find, that is the variation in tractive effort. Variation in tractive effort Ft is given by plus or minus under root 2 m omega square r 1 minus C. We will put the value of C, m is equal to 300, omega and r is also known. So we will get the Ft, that is tractive force, in plus or minus. Same way we can find the swaying couple by this equation, plus or minus L by root 2 m omega square r 1 minus C. This is the our final answer of the swaying couple. So in this way we will get swaying couple and tractive force Ft and our fraction C from the hammer blow equation. So this was the first example. Now I will take here, this is the second example. You can see in the second example there is data given. Following data refers to an inside cylinder locomotive. So here there is one inside cylinder locomotive where the mass of reciprocating part m is equal to 36 kg. Then the revolving mass, suppose we take it as m1, that is 16 kg. Then the total mass will be equal to m1 plus 2/3 of the mass. Here if the total revolving mass and 2/3 of the reciprocating mass are to be balanced, so this we will to take the total revolving mass is equal to m1 plus 2/3 of the reciprocating part or cylinder. So next it is given the pitch of cylinder, that is 700 mm, so that will be the our L. Then angle crank, it is 90 degree. Length of each crank, that is our radius, that will be equal to 320, that will be the crank radius, and we will convert into meter, so 0.32 meter. Next, wheel tread diameter is 1900, so the capital R radius will be equal to half of it, so it will be 950 mm, and we will convert in also meter, so it will be 0.95 meter. Again, the distance between the plane of wheel is given by 1800. Then that is the small a value, and velocity limiting speed v is given here, that is our 100 km per hour. We have to find the total, if the total revolving mass and 2/3 of reciprocating mass are to be balanced, determine the variation of tractive force Ft and Cs we have to find. So these are the given data as I explained. Now here this is the table, similar as the previous one. We will prepare the data, we will put the value balancing mass. We will first take A as the reference plane, and for reference plane the distance is L is 0, and there will be theta B1, MB1 is the balancing mass, RB1 is the radius which is unknown. This two is also unknown. So from couple polygon we will get one value, that is suppose this value we will get from the couple polygon. By taking under root of these two we will get that value. Here we can see over here, this is the position of plane and crank position. From couple polygon we can find the value of CD. So here we can easily find the CD. Then the velocity is given, so we can find the omega, which is equal to V by R, and hammer blow is given by this equation. We put the hammer blow equation, so from that we will find the variation in tractive force, as we know that the m omega square C, and C is given by this equation. Here we can see C is the 2/3, the only 2/3 fraction is given, so 0.66 is the value of C. We will put in the equation. So we can find the tractive effort Ft is given by this equation, plus or minus under root 2 m omega square r 1 minus c, and that is the tractive force equation. Similarly, we can find the hammer swaying couple. Swaying couple is given by Cs is equal to plus or minus L by root 2 m omega square r 1 minus c. So this is very simple example, easy to calculate. You can easily find the various values. So this is it for today's lecture. Thank you very much for listening me carefully. Have a nice day.